ongoing 5-day GYAN course on all about rectina, antenna, circuits, device, and applications. Today is the first lecture of this fourth day, which will be delivered by Professor Naoki Shinohara on the topic Theory and Technology of Rectina, Rectifying the Antenna for WPT. I welcome you, Professor, to start the session.
Thank you so much. So good morning. So welcome back to the day 4 of the ASEAN course. Today, I would like to introduce technology of the rectifying antenna. Here. Just a moment. I forgot it. Yeah. Yes. Switch. Yes. Good. Here. So in day 2, I introduced the radio propagation and the antenna technology mainly. And now you have a good technology to increase the beam efficiency in day 2. And yesterday, day 3, I introduced the wireless transmitter technology, including a semiconductor and a microwave tube both. We have a good beamforming technology, not only for wireless power transfer, but for the remote sensing technology. So there is a very big market on the remote sensing. And additionally, transmitter, of course, we have a very huge market for the wireless communication system. So if you don't know the detail of the wireless power transfer, you can learn beamforming technology and transmitter technology. But today's topic, rectifier, there is no market except the wireless power transfer. Because for remote sensing, of course, there is no receiver. We use a reflected radio wave only. And for wireless communication, of course, we have a receiver. But they use a demodulation circuit and they use information only on the carrier. And for wireless power transfer only, we need receiver, rectifier antenna named rectenna. So today's topic is most important, I think, so for the wireless power transfer. And especially day 1, I introduced the recent wireless power transfer business in the world. And especially in Japan just now, we established a new regulation of the wireless power transfer. And now this type, wide beam or ubiquitous type WPT are allowed in Japan. In this case, we don't need a special beam forming system because all power is distributed to everywhere, for example, in the room. And we don't need a very special transmitter because transmitting power is now very low. It's like a RFID system or the other. In this case, in ubiquitous type or wide beam WPT, rectifier, receiver is the most important technology to increase the received power. And additionally, on the lecture, today's second lecture, I introduced the rectenna for the energy harvesting. This is a permitted WPT system in Japan and in the world, and we put a special transmitter. So if regulation will allow us to use a higher power, we can use much power. But for the energy harvester, we cannot control the transmitting power and the transmitting radio wave. So in this case, importance of the rectifier becomes much higher, much more important. So at today's first lecture, I introduced normal rectenna mainly at first. And lecture 2, I introduced the suitable rectenna for energy harvester, low power and high efficiency rectenna. So please enjoy today's talk. So original word, rectenna, was created by William Brown. He combined the word of the rectifying antenna. So William Brown named this rectangle. And this is a very simple diagram, a block diagram of the rectangle. Of course, it is consisted of the antenna and rectifier. And usually we use a diode. But sometimes to make it small, in the MMIC or the other system, CMOS or the other three-port device is used. And additionally, to increase the efficiency, we must put the output filter and hopefully low-pass filter. So this is a simple diagram of the rectifier. And this is a world first rectangle, and it's patent by William Brown. He named rectangle, and he got the first patent of the rectifier microwave to DC converter in 1965. Of course, this patent has gone, but this is a very memorial rectangle developed by the William Brown, and it's his patent. And after his success of the rectangle, there are a lot of kind of the rectangle. And additionally, now I mentioned, we combine antenna and rectifying circuit. So first of all, I would like to introduce a various antenna because compared to the rectifying rectifier, we usually use the normal antennas, not only for WPT but also the wireless power transfer. So this is the world first rectangle developed by the William Brown. At the time, there was no microstrip antenna and microstrip line in 60s. So William Brown developed the rectangle with a simple dipole and a simple rectifying circuit. And the other group, for example, Intel's group developed the rectangle with a Yagi-Uda antenna. And the other group choose the spiral antenna, microstrip antenna, etc. So it means we can apply all antenna technology for rectangles. There is no limitation. So if you want to go to the you want to use a parabolic antenna, for example, of course you can use it. But usually for the energy harvester or the wide beam WPT, user requirement is a small antenna because mobility is most important for the radiative wireless power transfer. So unfortunately, we cannot bring the large parabolic antenna. So electrically and physically small antenna are required. And this is a general explanation of the small antennas. So this is original material by the Japanese famous professor, Professor Noguchi. And antenna size depends on the wavelength. Of course, it's very famous. And antenna size is specified by the radius of the largest sphere of the surrounding area. So this area is decided as an effective aperture. And electrically small antenna is smaller than Ka is equal to 1. Or physical small antenna is smaller than the something object and depends on the dimension. So there are a lot of small antennas here. And as I mentioned, day 1 or day 2, I forgot it, but hopefully we need a super gain antenna. Small physical antenna, but large electrical effective aperture antenna. But we cannot overcome the maximization. So unfortunately, in my understanding, we cannot develop the super gain antenna, except Yagi-Uda antenna. As you know, Yagi-Uda antenna is originally just a dipole antenna only. But in front and in back, on the back, we put the very simple metals. And as an effect of the metal and as an effect of the mutual coupling, simple dipole suddenly changed to the Yagi-Uda antenna, and antenna gain becomes 2 times, 3 times higher than the dipole antenna. But unfortunately, so Yagi-Uda antenna requires the height of the antenna. So usually meaning Yagi-Uda antenna is a super gain antenna, but it's not useful for the wide beam WPT or the energy harvester. So please change your mind from the antenna to the circuit. And of course, this is a rectifier. So we can use all rectifiers, half wave, full wave, bridge, or single shunt, etc. And of course, we can use all rectifiers for rectennas. But it's very important. Theoretically, 100% rectifier is most important. Because, for example, half-wave rectifier, we cannot realize 100% theoretically. Because this circuit here, only we can use the plus of the radio waves only in this half-wave rectifier. So if possible, we would like to develop a rectifier with a 100% efficiency. But if we choose a theoretically 50% rectifier, we never reach the 100% conversion efficiency. So first of all, we have to choose the rectifier with a theoretically 100% conversion efficiency. And especially in the radiative WPT, and historically, I recommend this single shunt rectifier. I'd like to explain why I recommend you to use this single shunt rectifier. And this is a typical RF-DC conversion efficiency of the rectenna rectifier. And this RF conversion efficiency theoretically, so limit is 100% as I mentioned. But this RF conversion efficiency of the rectifier depends on the input microwave power and the connected load. So if input microwave power is very small, here you can see this is a typical real diode VA curve. And if input power is very small, diode has the junction effect. In this very small voltage, diode is not diode, unfortunately. Plus and minus both pass through the diode. So in this low voltage area, efficiency is very, very low. And when we increase input power, efficiency increase because we can overcome the junction voltage. And but at last, if we add the very higher voltage than breakdown voltage, maybe you know diode has a breakdown if we add much power. And in this area, diode pass through the negative waveform. So if breakdown occurs, again, efficiency decreases. So this is a combination of the VJ effect and the breakdown effect of the RF-DC conversion efficiency. And additionally, diode is a nonlinear device. So if we pass through the radio wave into the diode, higher order harmonics occurs. And sometimes this higher harmonics will be reflected to the antennas. So a little bit efficiency decreases by the higher harmonics effect. So typically, here you can see we have an optimum microwave input power to realize the maximum RF-DC conversion efficiency. And additionally, when we change the connected load in the user, the same effect occurs. Because when we connect the very high load, for example, 1 kilo ohm or 10 kilo ohm, added voltage at the diode become higher because connected load is very high. So in this case, breakdown occurs. And connected load is very small. For example, 1 ohm or 0.1 ohm. Voltage at the diode is very small. And it's the same as a low input power region, and it's the same as a junction effect. So diode has a maximum, optimum input microwave power and optimum connected load. typically, for example, if we choose a Schottky barrier diode, so optimum input microwave power is about 1 watt below a few hundred milliwatt, and optimum load is about a few hundred ohms usually, in my understanding. So we have to consider how to create the optimum input power or optimum connected load. But user is not usually optimal. Usually user required, for example, 5 volt only, or we don't know the impedance of the user electronic circuit. So in this case, we need a DC-DC converter to stabilize the RF-DC conversion efficiency or stabilize the output DC voltage. And of course, we can use a commercial DC-DC converter, or sometimes we add the energy storage battery, etc., between user and rectifier. But usually DC-DC converter requests the extra DC source, power source, to drive the DC-DC converter usually. So, the day two I mentioned, usually, hopefully, user does not have any extra storage or battery. So, if there is no battery, how do we drive DC-DC converter? So this is our proposal by Kyoto University, self-powered buckburst converter. So we developed at first the rectifier around here, rectifier here, and we use some part of the rectified power to drive this buckburst converter. So it means we share the rectified power. One is to user, and some part of the rectified power is used to drive the DC-DC converter. And we developed it without any extra power source or extra battery at the users. So as a result, this black line indicates a normal RF-DC converter of the rectifier, as I mentioned before. And if we add this self-powered buckburst converter, this RF-DC curve suddenly destabilized here. Of course, this buckburst converter has some loss in the circuit. So totally, unfortunately, peak RF-DC conversion efficiency decreases a little. But around here, for example, very high load area or around there, we can increase the RF-DC conversion efficiency, and a very stable RF-DC conversion efficiency, we got it. So this is our proposal from Kyoto University. Of course, if you don't have enough time, you can buy the commercial DC-DC converter or the other. But we, Kyoto University, developed this self-powered buckburst converter for the rectifier to stabilize the RF-DC conversion efficiency trend. And here, I'd like to introduce a very basic theory to develop high efficiency rectifier at the optimum input power. Here, we would like to increase this maximum optimum RF-DC conversion efficiency, hopefully close to 100%. So this is a very, very simple theory of the diode circuit. This theoretical limitation of the RF-DC conversion efficiency was read by the Japanese famous professor Takashi Ohira, and he chose these rectifiers, so single series, single shunt, bridge, double voltage, etc. And if you have a time, please check this paper, and the detail is written in this paper. And as a result of this analysis, he reached this conclusion. Single series or single shunt rectifier, we can reach theoretically about 80%. And bridge or the other rectifier, we can reach the theoretically 92%. But I suppose you consider, for example, bridge is very simple. If we have a bridge rectifier, theoretically it's 100%. But why he could not reach 100% theoretical efficiency? It means he didn't involve harmonic effect. So as a DC power, even if we choose a bridge, which theoretical efficiency is 100%, only the 90%. And the rest 8% is a harmonic or fluctuated power. So this is correct theoretically. But now he didn't reach the real theoretical 100% rectifier, even with a bridge diode. So next, we have to consider how to increase the efficiency theoretically 100%. Oh, I forgot it. This is a real measurement data of the real radiation of the harmonics from the diode. Of course, this harmonic power is not much, but these harmonics are very, very important to increase the efficiency to the 100%. Please go back to the yesterday's talk. We use harmonics resonator to increase, to realize 100% amplifier circuit. It's a same. We need to use these harmonics to increase the efficiency even at the rectifier. So this is a very old but simple and excellent rectifier named a single shunt rectifier proposed by I suppose William Brown. And in parallel, the other group in New York University of the etc. in 70s, they developed this operation of this single shunt rectifier. Single shunt means diode is installed in series, and we use only one diode here. And if we use only one diode, it seems a half-wave rectifier because diode is just a switch only. So if diode is on, of course, microwaves pass through the diode. But if diode is off, unfortunately, all microwave power is cut at the diode. So usually, one diode rectifier becomes is a half-wave rectifier. But this is a secret. We do not install this diode in parallel in the circuit. So instead of the parallel diode, we install this diode in series. So in this case, a diode has a switch on and off. Line is connected directly the users. This is one secret. And the other is here, quarter length distributed line, and usually capacitance. And based on the day one equivalent circuit theory, we can estimate the input impedance from this area to the connected load side. And when we install the quarter length distributed line and the capacitor, we get this input impedance. And if we can assume capacitance is very high, enough high, hopefully infinity, and this input impedance becomes infinity for the infinity open for the odd harmonics, and zero short for the even harmonics. Because this quarter length is for the main main frequency microwave only. So if for the harmonics, second harmonics, its wavelength becomes half. So for the second harmonics, this quarter length distributed line becomes suddenly half wavelength distributed line. And for the third harmonic, for example, 3/4 quarter length distributed line, etc. So effect of this quarter length distributed line for the main frequency for even and odd harmonics, we can create the relationship of the impedance infinity and 0. So please go back to the yesterday. This relationship is exactly same as a class F amplifier. So as a result of this combination of the resonator circuit, only with a quarter length distributed line and the capacitor, we can create this form with the current and voltage at the diode. So maybe you remember this form of the current and the voltage is exactly same as amplifier, class F amplifier on the FET or the HBT. So based on this output filter combination of the resonator, as a result, we can realize this relationship of the waveform as a current and the voltage, and as a result, theoretically, we can reach 100% conversion efficiency. So this paper, professor in New York University described the detail of this theory. And so please go back. So this form at the diode on the single shunt rectifier is exactly same as this class F. But here you can see, I showed you the same figure yesterday. And for example, if we use only even current harmonics, it becomes an ideal class B amplifier. And Professor Ohira's theory explains this type. It's very close to the rectifier of the right class B. So efficiency is very close to the for rectifier and for amplifier class B. And now I introduce the single shunt rectifier with the help of the theory of the class F amplifier. We can reach this 100% theoretical conversion efficiency. So please consider, please think amplifier design to design the rectifier. This is my proposal. And so in advance, we Kyoto University consider now we need one assumption. C capacitance is needs very high value. So if possible, capacitance is small. So this assumption is not a good assumption theoretically. So we Kyoto University consider directly we put the similar peacock wing as a resonator for the class F amplifier, and we developed the just the same class F rectifier. And at the time, we developed this class F rectifier at 24 gigahertz, and efficiency was enough at this millimeter waves. And the other group consider sync amplifier design I explained now. So the other group consider, for example, class B, C, and yesterday I introduced you class D, E, etc. So there are a lot of interesting rectifier. For example, this Spanish group showed us class C rectifier, they said in this paper. And this is a class D rectifier developed by the British Columbia. And maybe you remember there is a push-pull circuit here, and we add the series resonator here. This is the same as the class D amplifier. But instead of the three-port devices, we put, in this case, CMOS, but it is considered as a diode. Of course, next we have class E. it's the same as a class E amplifier. Of course, instead of the three-port device, we put a diode or the CMOS, etc. And so now we have class C, D, E, F rectifier. And in near future, I suppose class J or R rectifier will be born. It's the same as an amplifier design. And additionally, same as amplifier design, famous professor in Colorado University, Jay Popovic, has already developed power amplifier rectifier. Because for the power amplifier, of course, we use a three-port device, but explanation to amplify the microwave or to rectify the microwave is very similar, as I now explained. So if we change the input port and the output port, theoretically, we can use the same circuit, once for amplifier and once for rectifier. So she did it. Once she designed this amplifier at first, and this is originally class inversive amplifier she designed. And next, she changed the input port and the output port. And as a result, this exactly same circuit is changed to rectifier and class inversive. So in this case, we can develop the same circuit both for transmitter and receiver. Sometimes in the inductive wireless charger, they develop the simultaneous transmitter-receiver system in low frequency. But her technology is very excellent. Now we have a good technology both for amplifier and rectifier in the same circuit. So as I explained again, please think amplifier design to design the rectifier. So this is a very excellent evidence. Amplifier design and rectifier design is the same. And this is a theoretical estimation of the equivalent with the equivalent circuit of the diode. And here, this is a typical equivalent circuit of the Schottky barrier diode. And based on this equivalent circuit and equivalent circuit design, and Professor Kai-chan group, day one, I introduced the past famous US research in 90s. And he introduced these formulas. And if we have this formula, it's easy to understand the theoretical RF-DC conversion efficiency with a real diode. And it seems a little bit complex, but when you have an Excel or the other software, we can estimate simply the RF-DC conversion efficiency with your choice diode, for example. And based on this theory, Professor Kai-chan group showed us the theoretical RF-DC efficiency curve depends on the figure of merit. Omega RC. R is the internal resistance of the diode, and the CEF is the internal capacitance of the diode. And as you know, in the circuit capacitance, we should use the capacitance as a J omega C over 1 over J omega C. So we must add omega, angular frequency. So, and based on previous theory, figure of merit is omega RC. So, and omega RC becomes large, efficiency becomes small. It indicates a very important point. Of course, it's easy to understand. Internal resistance of the diode is very large. Efficiency decreases. Efficiency becomes very small because diode is a loss factor. But The other important point, capacitance. If diode has a large capacitance, efficiency degrades. Usually, capacitance doesn't include the loss factor, but this capacitance creates a phase difference between the voltage and the current. So as a result of the phase difference of the voltage and the capacitor, efficiency decreases. Additionally, omega is a very big parameter. So I mentioned sometime in this course, when we increase the frequency, circuit efficiency decreases. And by formula, this is a good evidence. When we increase the frequency, efficiency decreases. So please remember this formula. And it's easy to estimate the RF-DC conversion efficiency with your choice diode. And this is a recent developed rectifier with the output power and efficiency. So as I mentioned, now when frequency increases, power and efficiency decreases. But as I mentioned before, we are engineers. We cannot overcome the Maxwell's equation and we cannot develop the super gain antenna. But as an engineer, we can develop a good semiconductor, good diode, and a good circuit. So this strength can be improved in near future by ourselves. It's engineer technology. And the other viewpoint, impedance matching. Of course, it's very important to design the rectifier. And important point, if we change the connected load or the frequency, etc., on the Smith chart, this impedance always changes. So there is only one point as a impedance matching point in the rectifier, because a diode is a nonlinear device, or we have the other characteristic of the equivalent circuit. So this matching point is only one. It's very important. So when we change the input microwave power or frequency or connected load, unfortunately, impedance changes and some reflection occurs. And this is a real measurement data of the reflection. For example, when we change the connected load in user, efficiency changes and reflection reflection occurs, for example. In this case, when we connect a very high load, high impedance load, reflection rate reached close to 40%. So it's not good. But when we consider the optimum connected load, the optimum input power, efficiency has a peak and reflection rate becomes very small. So this is a very important figure to explain the reflection or the impedance matching of the rectifier. So I summarize how to increase the efficiency of the rectenna. First of all, most important, choose a theoretically 100% circuit. Please don't choose half-wave rectifier. And this is the other point. Reduce the number of the diode, because diode involves a loss factor. So I recommend you to use single shunt rectifier, because only one diode can achieve the theoretically 100%, as I explained now. And of course, a diode is the most important factor to decide the efficiency. So please choose a diode with a low omega RC, not R, not internal resistance. Capacitance is also very important. It's a very important point. And of course, impedance matching, we have to match. Of course, not only the rectifier, but also the amplifier, etc. And design circuit with a higher harmonics combination like class F. So, of course, we can read the theoretically 100%, for example, class C amplifier, for example. But it's easy to understand when we add the other output filters, like class D, E, F, we can read theoretically 100%. So I recommend you to use the class F circuit like a single shunt, etc. Additionally, we can separate the unexpected higher harmonics re-radiations. And the other point, at the high voltage, almost breakdown voltage. So this is the other viewpoint, not circuit problem, but even if input microwave power is very small, but we have to combine voltage and current from the power. And the voltage is very important. So even if my input microwave power is very small, but if we can convert the higher voltage, we can increase the power. This is the second topic today for weak powered rectifier, low for energy harvester. And additionally, please don't forget, combination of the antenna is the other important point. So next, I would like to introduce the theory and technology of the antenna again, because so as I mentioned in day 2, theoretically based on the Friis transmission formula or Maxwell's equation, even if we can increase the antenna radius or shorter distance or higher frequency, theoretically by this formula we can reach about 100% beam efficiency. So even if 36,000 kilometer distance WPT system named the solar power satellite, we can reach about 90%, 99% but with a very large antenna size. But please don't forget antenna itself, especially if you know the antenna technology. Sometimes very famous antenna professor told me receiving efficiency at the receiving antenna is theoretically 50%, they say. If we have an antenna as a receiver, famous professor told me, input radio wave will be reflected 50%. So half of the input power will be reflected, professor told me. In one viewpoint, it's correct. But for the large array rectifier, array rectenna, it's not correct. I would like to introduce now. 100% we can realize it. So this is a basic theory of the phase array theory and the diamond stack. It's very, it's very old theory in 40s. And we consider infinite array, first of all. And we put a lot of antennas. There is no rectifier, just antenna theory. And when we develop the infinite array there, next we should consider impedance matching between the array antenna impedance and the space impedance, 125. And based on this equation, they calculated the impedance or the admittance of the infinite array. In this case, they choose a slot antenna, for example, and they change this formula again and again. And sorry, I cannot explain the detail here, but as a result, receiving efficiency is as follows here. And from this theoretical efficiency at the receiving antenna, this we got this figures. And in this equation, theta is a beam input angle to the array antenna. So when this is a parameter of the antenna spacing of the x-axis and the y-axis A and B, and we change the radio wave input direction to the infinite arrays. And when we input the directly from the front beam, efficiency reaches 100%. If element spacing is enough small, close to up to one wavelength. And of course, if we put the antenna with a large antenna spacing, of course, there are some space without any effective array, and efficiency suddenly decreases. And when beam angle, input beam angle changes, for example, 30-degree and 40-degree, of course, impedance of the array antennas changes by mutual coupling. So efficiency decreases. But if we choose optimum element spacing and front beam, we can reach the 100% receiving efficiency at the receiver, not 50%. So this is a theoretical estimation. And the other Japanese group carried out the other R&D. Instead of the slot antenna, they applied a microstrip antenna. And they read the similar equivalent circuit, and they read the same figure. And in this paper, they carried out this formulation without loss and with loss. This is antenna losses. Of course, if antenna has a loss, real loss, resistant loss, of course, efficiency cannot reach 100%. But if there is no losses in antenna, we can receive all input power into the circuit. So, famous antenna professor is not correct. So we can receive reach 100% radio wave into at the receiver. This is a formulation result. And in my Kyoto University, I could not believe it. Of course, this is just a formula only. So we simulated by the FDTD electromagnetic computer simulation. And this is our result. In front, we transmit a plane wave in this case, and we put the infinite array there. And we consider this antenna is a reflected, a diode with a reflected plane. And at first, a very small reflection occurs. But in a stable state, here, antenna receives all power, and my student estimated receiving efficiency as a receiver reached 99.9%. So beam efficiency, so day 2, I explained to you, theoretically we can reach 100%. And at the receiver, we can reach 100%. So in the narrow beam WPT, we can realize 100% efficiency from the antenna to antenna. And additionally, in the other group, Japanese group, carried out experiment. So they developed this antenna with rectifier, and they developed variable spacing rectenna arrays. And they estimated a very similar formula, and they carried out an experiment. So at last, receiving power, receiving efficiency reached close to 80%. Of course, this is a real experiment that it involves antenna loss, etc., or error, but not 50%. So they reached about 80%. It means 50% theoretical receiving efficiency is not correct. So we can reach, if we have a no loss antenna, we can reach 100% receiving efficiency, even in experiment. So this is, I explained to you now, theoretical efficiency of the transmitting beam efficiency and the receiving antenna efficiency. So please believe me, theoretically, we can reach 100% WPT systems. And last 5 minutes, I'd like to introduce the recent very good rectifiers in the world. So this is our rectenna, Kyoto University rectenna. My student, PhD student, develops a rectenna at UHF frequency 930 megahertz, and he proposed the very novel design method, very similar to the amplifier, load pull or sword pull method we have to design the amplifier. And he adopted this load pull or source pull design method, and he proposed these additional circuits And as a result, he reached 91% at the UHF frequency. I think this is a current world record of the UHF rectifier. And the other, about 10 years ago, we Kyoto University has a collaborative research, and at that time, we've already reached over 90% rectify RFDC conversion efficiency at S-band, 2.4 gigahertz. And the other PhD student developed the other type of the rectifier, and he has already reached 91% at the S-band too. And recently, Japanese group, Kanazawa Institute of Technology, Professor Ito's group is very, very famous to develop a very good rectifier. And they developed same as 90% RF conversion efficiency rectifier at 2.4 gigahertz. And he likes the bridge rectifier. We like the single shunt, but he always used the bridge rectifier. And additionally, for the energy harvester, they developed a very interesting rectifier with high impedance dipole antenna and high impedance circuit. This is the other topic in my second talk today. So this is a low power rectifier with a higher low power rectifier with a higher impedance, and they reach over 90% at C-band, 5.8 gigahertz. And in parallel, they developed MMIC, and to develop the MMIC, a little bit conversion efficiency decreases, but it's enough at C-band, close to 80%. And we, Kyoto University, developed a Class F amplifier, as I mentioned before, and we've already reached about 80%, I don't know, 50% with MMIC and the Class F rectifier technology. And the other Japanese group, Tsukuba University, they developed very high efficiency double band, 24 gigahertz rectifier, and at that time, efficiency was very poor, so there is no data of the efficiency, but about a few percent only. But I suppose this is the first rectifier at the W band in Japan. And the same frequency band, Raytheon Group has already developed 61 conversion efficiency at this W band with help of the new gallium nitride technology. And the same Tsukuba University group develops a 300 gigahertz rectifier. And of course, efficiency was quite poor, but I suppose this is only one rectifier at this such, so like a terahertz radio waves. So this is the current world records in my understanding. And so I think based on this today's lecture, you will develop the better rectifier for in near future. So that's all my first talk. So thank you so much.
Thank you very much, Professor Naoki, for this first session. Now it is open for discussion. Any query from the participant side?
Good morning, sir.
Hi.
Sir, I would like you to shed some light on the ubiquitous WPT.
WPT. You mean this one? Ubiquitous.
Yeah, that I understood. Like, you said about energy storage for WPT, right? So I want to know regarding, is there any possibility for energy harvesting for WPT applications?
Yeah, of course. So only one weak point at energy harvesting is very tiny ambient radio wave only. So of course I agree. We need energy storage or battery, or but if possible, so battery-free IoT device is better for user. So in this case, we avoid the battery storage, and instead of the battery storage, we'd like to develop a very good rectifier. And so sometimes, so then we expand we can develop some high efficiency. So, but so of course, it's your choice. If so supercapacitor or battery or the other energy storage, we can use it. And some, for example, combine the solar cell and radio wave energy harvester, etc. So we can use as a, but I don't have a good energy storage technology, unfortunately.
Thank you. Arigato.
Any other query? Any more query? Let us have a tea break. We'll meet again at 11:10 for second lecture of this fourth day. Thank you.
Yes. All right.